Okay, yeah. Hi, everyone. I'm Harriet. I'm talking about ggdibbler today. This is work I've done with my supervisors as part of my PhD project at Monash University. So, what is uncertainty visualization? Pretty reasonable question. Let's imagine that you're me and you decide to do a very big research topic, which is a broad and undefined issue of uncertainty visualization. And so you kind of are dropped in, off you go, hit the ground, not happy about it. And then you're kind of confused because you're like, well, I don't really know what this is. There's like distributions and there's like spaghetti plots and there's a lot of different plots that are all kind of fitting under the like phrase of uncertainty visualization. But the connection between them is not always super clear. But it's okay. You have an industry partner who actually proposed this project. So you go, okay, I'll just ask them. You go, hello, excuse me, industry partner. I'd like to know what the point of this project is. And they come down from the heavens to tell you to research uncertainty visualization. And you go, okay, what specifically do you mean by that? Can you be a bit more specific? And you just kind of wait. Maybe you'll get an email back eventually. And they actually don't know. They're like, well, I don't really know, but I just don't really want my graphics to be able to lie to me. You know, I think that's kind of the general sentiment. Okay, still vague, but this is something I can work with. This is a goal that we're working towards. And we're going to work through this with an example. So, can a graphic lie? Well, we're going to look at an example where we've got the Bureau of Meteorology has identified some weird temperatures in Iowa. There's a strange spatial pattern in the data. And we're going to get some citizen scientists to measure their data and report back. Not so fast, though. Science in Iowa is now illegal. So we need to maintain anonymity for our lovely citizen scientists. And we can only provide the county-level data for each scientist. So we have data that kind of looks like this. Scientist number, county, and a recorded temperature, and we have about 900 participants. Okay, so we need to look at this data. We want to be able to see that spatial trend we were talking about. And we want, with bringing in the line thing, we kind of want the confidence we have in that spatial trend to be in line with the statistical, quality of that conclusion. Okay, this approach though, which is visualization, doesn't just need to work for statisticians, it needs to work for a lot of people. It needs to work for your average Joe. And it also needs to work for someone like my mother, who is largely wildly untrusting. This is a real text I got from her. This is about the Australian government, by the way. Not the American government, so I don't know what her problem is. But it doesn't just need to work for my mother, it also needs to work for me. That's a text I sent when I spent $500 on Tamagotchis that didn't exist because I tried to buy them with an Amazon gift card from someone on Facebook Marketplace. In hindsight, obviously a scam, but I'm too trusting. We're two opposite ends of the spectrum, but the visualization needs to work for both of us. So that's a summary, right? This is what we're trying to do. We want my mum to trust the results, so we need to be reinforcing justified signals, be providing evidence that they're true. But we also want to hide signals that aren't true because I will latch onto them because I see things that aren't real all the time, such as pseudo-Tamagotchis. You can also kind of think of this as like a statistical test, of for a visualization. You want to be able to extract signals that are real when they're there, and you don't want to be able to see the signal when it's not there. Okay, so first things first, you can just plot the data. Just because it's all on the same spot and we just have the county level, that doesn't mean you can't plot the data. And there it is, that's the data of our citizen scientists. Very regular, just like Iowa's counties. It's very nice. And there's benefits to this, plotting original data can it can reveal some of the limitations of our data, It can highlight when we have a small sample size, irregular sample sizes, high variance, missing values. These are all things that we see often when we plot our raw data. But understanding these limitations can, in a way, hedge those conclusions. But we don't always have the original data. The original data isn't always available. It's not always relevant, and it's not always deterministic. Sometimes we get anonymized data from a government. Sometimes we need to use the sampling distribution because what we care about is a difference in averages or estimates. Sometimes you just have deterministic values, you know, and it's not deterministic, sorry. And they're estimated or you've got bounded values, you know. And so if we go back to our example with the Bureau of Meteorology and the Iowa citizen scientists, they let us know that they're only looking for the average values of counties. So now we're looking at the sampling distribution. We do not have this data for the sampling distribution. And usually, you know, I'll show you how we usually do it, which is that we kind of don't really bother with the uncertainty. We've got our data, we might combine them into the county names, we'll get an estimate of the average for each county, and we'll just plot it with a choropleth map, you know? There it is. And we can see that there's kind of something there. I mean, hopefully you guys can see that there's something there. There's some kind of pattern, but we don't really know how valid it is. We don't know how much the variance changes between the areas. And so what if the area is a little worse than that, maybe? You know, maybe we think that the error there is fine, but how bad can our error get? So it turns out some of our citizen scientists were using very improper tools, and the standard error could be up to 3 times the error that we originally estimated. And so the Bureau wants to see both cases. How bad is it if, you know, the error gets really bad? And these, the 2 plots, one of them is for the high variance case, one of them is for the low variance case. I will save you time. They are identical if you were looking for a difference. A choropleth map does not have a way to kind of integrate any kind of uncertainty or any variance, so I don't know what you guys are looking for. So how do we make this plot a little bit more honest? You know, first, and this is usually the most obvious and kind of the initial thought is, okay, what if we just add an axis for uncertainty? You know, color is 3 dimensions. Don't quote me on that. And, you know, we can now see that there's a difference between the 2 plots. That's nice, hey? We've got a little bit of transparency. We've got the case where there's the low uncertainty, and you can kind of see that there's a little bit of a wave pattern, not to give it away. But you can also see the high uncertainty case. You can see that it is visibly different to the low uncertainty case. Problem is, does this work? Not really. Well, what has it failed to do? It has successfully included uncertainty. There is technically uncertainty in the graphic, and if you do go and look at the legend, you can see that it is a highly uncertain plot. But I can still see the false signal. If we go back and look at it, you can still see the wave pattern. So I'm still getting scammed. There's a second issue, which is that there's a 2D palette involved, and 2D color palettes they're not really as simple as 3D color spaces. It's not like linear like in physical spaces, and so it's a bit more difficult to maneuver. And it's also not accessible. That there is Susan, one of my supervisors. She is colorblind. She doesn't like this plot at all. She can't really see what's going on. Next meeting is very difficult. Okay, so as an aside, why doesn't this work? Why can't we just add an axis, you know, that says uncertainty? And it's because uncertainty isn't really just another variable, you know. It presents an interesting perceptual problem for uncertainty visualization that I think has largely been unexplored. Well, a little bit unexplored. Usually, we don't want variables to interfere with each other. Usually the goal when we plot 2 variables is you don't want plotting y on your scatter plot to all of a sudden make x unreadable. That would be a very bad plot. But uncertainty visualization is kind of the opposite. If we want that approach where we can see it when the signal's valid and we can't see it when the signal is not valid, we do want the uncertainty to interfere with the signal of the plot, or the estimate, you know? And so that's kind of the core of the signal suppression approach that we're taking to uncertainty visualization, which is that we want to hide those invalid signals. So you might say, okay, what if we manually interfere them? You know, what if we do this? And this is called a value suppressing uncertainty palette. This is designed by someone who I can't remember. But now we're going to blend the colors together. And, you know, you can see the low uncertainty case. We can still see the pattern. That's what we want. And the signal is now hidden for the high uncertainty case. You might be thinking, that's good. That's what we wanted. Job done. Not quite. While me and my mother are both very happy with this plot, we still have a few issues. One, the 2D color palette's still there, which means it's still inaccessible. There's also no rule for when to blend the colors. So it's like, you blended it when the standard error is 1, 3, 7? Like, it's not really clear. Do you have it fail a t-test? If you have it fail a t-test, but hypothesis tests aren't all ubiquitous, like, You can fail a F test and pass a T test. It's kind of a bit all over the place, so it's not really sure when two colors should be the same. Okay, so now we're gonna go, okay, forget the color palette thing. What if we just simulate a sample and then maybe implicitly you will hide the signal? And so you can see that we've got the low uncertainty case, the signal is visible. I think the high uncertainty case is a little harder to read, but I have gotten mixed reviews. So you can kind of see though that there is a visible difference and it is maybe a little bit different. This might be related to how I simulated the data, is that you can still see it. But does this work? Kind of. Who can say? It's hard to say. This is the kind of thing you need perceptual experiments for. You know, we've included the uncertainty. You can't see the high uncertainty has at least created some kind of interference. We've got a 1D color palette. The problem is this plot was a complete nightmare to make. Why are these plots nightmares to make? All of the plots shown in this talk so far have been complete nightmares to make. Well, it's because there isn't really, well, there wasn't really a way to store uncertainty back when these packages were made. So these are like 5, 10 years ago, some of them. Some of them are more recent, but you know, we want to be able to, the philosophy behind these visualization implies that we need a way to store uncertainty as a single value, you know, store a distribution within a table. And so it's best to represent uncertainty usually as a distribution. It kind of seems to encompass most of the methods. It should take up one cell and it should set up a vectorized, so I'm thinking, right, when I'm working this out, I'm thinking, oh God, am I gonna have to set up some kind of vectorized distribution object? Sounds like a nightmare. I don't have time for this. I don't want to do this. Thankfully, I didn't have to. It turns out Mitch, who's speaking next, did it for me independently several years earlier. So yeah, this is what we have. We have a tidy version now of distributional data where we can have, we group by the country, and now when we do the summary, instead of just taking out the mean, we're gonna format it as a distribution. We're gonna have a mean, and then we're gonna have our standard error, you know? And so what does this package do, distributional? Is it just let you hold these normal distributions? It's got a little bit on it. First of all, it's classing our data is now officially a distribution. It's a distribution object, so it can do a lot of stuff that distributions can do. You can also mix different distributions. In this example, they're all normal distributions, but you can have lots of different types. And you can also have a sample rather than just a strict distribution. You can do it through bootstrapping or something. So what happens if you don't use distributional? What do we get? Like, what if we tried to build this up without this kind of tidy distribution package? Well, there are previous examples. I'm going to go through VisuMap, which, not pointed out, I do like VisuMap, but it's just the code for it is a little bit difficult because it was made without the distributional package. It makes these bivariate maps and it makes the pixel maps, but also a lot of these packages that make a lot of these plots, they're bespoke. They're not really in the ggplot framework. They are plots that you code up independently and you have to build all these different functions, and you get a ggplot object at the end, but it's not really clear that it is a ggplot object. You don't really get the nice flexibility that you get with a ggplot. So let's look at the code that was used to make this original pixel map. So you've got the pixel map code. This is the ideal pixel map code. This is what I would like the pixel map code to look like. I would like it to be a ggplot. I would like to do the normal geom-SF, but I would like it to recognize that I have put a random variable in one of the axes, and then I would like it to just kind of automatically fix it, you know? Maybe I have options for some of the ways it's displayed, but in general, I would like to just be able to, you know, throw it all in there and not think about it. That's not what you have, actually, if you use VisuMap. So first you have to do the formatting data using bespoke. You have to make your bespoke data with the specific formatting function. You need to pixelate your shapefiles. You need to run that through a different data processing. Then you need to build the pixel map using the specific build pixel map file function. And then you need to have a specific view pixel map function that you use to look at it. So it's very not similar to the tidy ggplot code that we're used to. Okay, so can we plot the pixel map now? I mean, we've got this distributional object. Can we just throw it in there? You know, No, we can't. We need to extend ggplot, unfortunately. ggplot uses the grammar of graphics. We've all seen it. We've all talked about it. But a key part of the grammar of graphics is the fact that it's designed to take in data. It is not designed to take in distributional objects, theoretical distributions. You do not get a ggplot at the end if you feed it in. You will get an error, and it's very sad. So that's what kind of the point of ggdibbler is it lets you feed in distributions into ggplots, and it should adjust the plot and try and create a signal suppression, or try and create a signal suppression plot. That's ggdibbler. So that's the hex sticker. It was named after an Australian animal called the dibbler, because my supervisor, Di Cook, likes to name packages after Australian animals. I also picked that animal because I wanted it to be next to the ggdist package alphabetically, because ggdist also uses distributional to plot distributions. And the fact that a dibble would be a distributional tibble didn't even occur to me. But I got that for free. Here it is. This is how it works. You have geom_sf, and then you have to run the sample. I don't have a dibble object yet. And then you have your geometry. You put in a distribution as a fill option, and that's the default plot. That is very similar to the default plot you get if you just run geom_sf. And it's got all the bits and bobs that you can edit with the normal ggplot stuff. You can add in your labels, and you can change the number of samples. You can change the scale. You can change the colors. You can customize it. You can do whatever you want. It's important to note, though, that the plot is generated from a random sample from your distribution. So if you run it again, you'll get a slightly different plot. And that is basically all the ggdibbler is at the moment. I took leave between submitting this talk. There's several months of leave between submitting this talk and presenting it. So this is what I had when I submitted the abstract. We have the plan for the future is to implement different other alternatives to other geomes, maybe expand a bit of the geom_sf stuff, introduce a dibble object as well as on there. Integrate. And if you have suggestions or you have a specific thing you would like to have added, you can put in an issue. I might get to it eventually. At the current rate that they're increasing, probably not, unless I give it a high priority, and I think that's neat. These are some of the current issues and some of the current plans for the package. If you care about software and you want to go look at it or download it or complain to me personally and send me an email about how much you hate it, you can go to the GitHub. And if you care about the theoretical aspects of it, there is a paper that kind of outlines the signal suppression approach if you're interested. And that's it for me. Yeah, thank you.